Welcome to the session on Karlpearson's coefficient of correlation. Myself Josmi Joseph, Assistant Professor of Computer Science. Here we are going to see the second method of finding the correlation coefficient, which is Karlpearson's coefficient of correlation. Correlation is a statistical tool which studies the relationship between two variables in a bivariate distribution. Correlation analysis involves various methods and techniques used for studying and measuring the extent of the relationship between the variables. In the previous session, we have already seen different types of correlation like positive and negative correlation and linear and non-linear correlation. And methods of studying correlation also we have seen scatter diagrams, Karlpearson's coefficient of correlation and Spearman's rank correlation. The method of scatter diagram about the nature of the relationship, whether it is positive or negative and whether it is high or low. It does not provide us an exact measure, a numerical measure of the extent of the relationship between the two variables. That is why we are going for Karlpearson's coefficient of correlation and Spearman's rank correlation. So here in this session we will be discussing Karlpearson's coefficient of correlation. This is also known as product moment correlation coefficient or Pearsonian correlation coefficient or simple correlation coefficient. And this method is used only when there is a linear relationship between the variables. When there is a non-linear relation between the variables, calculating this correlation coefficient may be misleading. Correlation coefficient between two variables x and y is a numerical measure of the linear relationship between the variables. It is denoted by r of xy or rxy or r. And it is defined as the ratio of the covariance between the variables to the product of the standard deviations of the variables. Suppose we have n pairs of observations x1, y1, x2, y2, etc. xn, yn. Then the correlation coefficient is covariance of xy divided by standard deviation of x into standard deviation of y, where covariance of xy is equal to summation of x minus x bar into y minus y bar divided by total number of units n. And sigma x, the standard deviation of the variable x, is square root of sigma x minus x bar square divided by n. And standard deviation of y variable sigma y is equal to square root of summation of y minus y bar square divided by n. By substituting the values of these equations of covariance and standard deviations, we can have other variations of the equation. Substituting the formulas for covariance and standard deviation, we will get r is equal to sigma x minus x bar into y minus y bar divided by square root of sigma x minus x bar square into sigma y minus y bar square. Now another formula is r is equal to n into sigma xy minus sigma x sigma y divided by square root of n into sigma x square minus sigma x the whole square into n into sigma y square minus sigma y the whole square. So based on the given values, we can use any of these three formulas for calculating the correlation coefficient. Now let's see with examples. Calculate Karlpearson's coefficient of correlation for the following. For this is a bivariate distribution. Here we have the x values and y values. We are preparing a table like this. First, the given x values and the sum of all these sum of all the x values is 30. These are the given y values and sum of all y values is 40. Now calculate the mean x bar, mean of the variable x. So sigma x by n, which is 30 by 5, 6, and y bar sigma y 40 by n 5 is equal to 8. Now find x minus x bar. So you will get this column and find the sum of x minus x bar. Now find the square of this. You will get this column. Find the sum of all these. This is sigma x minus x bar square is 40. Now find y minus y bar. Y minus y bar is 8. So y minus 8. So you will get 9 minus 8, 1, and 11 minus 8, 3, and so on. And this is sigma of y minus y bar. Now take the square of this. You will get y minus y bar square and find the sum of all these. This is sigma y minus y bar the whole square, that is 20. Now find the product of x minus x bar and y minus y bar. So 0 into 1, 0, minus 4 into 3, minus 12, and so on. And find the sum of all these. You will get minus 26. Now by substituting these values, sigma x minus x bar squared, sigma y minus y bar squared, sigma x minus x bar into y minus y bar in the formula for correlation coefficient, will get, we have sigma x minus x bar into y minus y bar is minus 26, sigma x minus x bar square is 40, and sigma y minus y bar square is 20. So by substituting the values in the equation, r is equal to sigma x minus x bar into y minus y bar divided by square root of sigma x minus x bar square into sigma y minus y bar square, will get r is equal to minus 26 divided by 40 into 20. While calculation, you will get minus 26 by square root of 800, which is minus 0.9192. This is a negative correlation and the value is almost near to minus 1. So this is strong negative correlation. Another example, the coefficient of correlation between two variables x and y is 0.48. The covariance is 36. The variance of x is 16. Find the standard deviation of y. So we are given with the correlation coefficient and the covariance and the variance of x. So r is given, the coefficient of correlation is given as 0.48 and the variance sigma x square. The variance is the square of the standard deviation of the variable x is 16. So from this we will get the standard deviation of x as square root of 16, which is 4. So now covariance of xy is given as 36. Now we have the equation for coefficient of correlation r as covariance of xy divided by standard deviation of x into standard deviation of y. So from this we can calculate the standard deviation of y by substituting the values of covariance of xy and standard deviation of x. So now we will get sigma y is equal to covariance of xy divided by r into standard deviation of x, which is 36 by 0.48 into 4, which is 18.75. So the standard deviation of the variable y is 18.75. Another example, calculate the coefficient of correlation between x and y series from the following data. For the series x and y, the number of pairs of observation is 15 each. Arithmetic mean of x series is 25 and arithmetic mean of y series 18. Standard deviation of x series 3.01 and that of y is 3.03. Sum of the squares of the deviations from mean. Sum of the squares of the deviations from mean is sigma x minus x bar the whole square is 136 and sigma y minus y bar square is 138, and the summation of product deviations of x and y series from their respective means is 122, that is sigma x minus x bar into y minus y bar is 122. So what is given here is total number of units n is 15. Arithmetic mean of x series is x bar is equal to 25 and arithmetic mean of y series y bar is equal to 18. Standard deviation of x series sigma x is equal to 3.01 and that of y series sigma y is equal to 3.03. And sigma x minus x bar square is 136 and sigma y minus y bar the whole square is 138. Sigma x minus x bar into y minus y bar is 122. So from this we can calculate using the formula sigma x minus x bar into y minus y bar, which is 122, divided by square root of 136 into 138. So we will get the value of the correlation coefficient as 0.8905. Here we have already given with the standard deviations of variable x and y. So we can use another method also. So here by substituting the values for the equation covariance of xy divided by sigma x sigma y, first we can calculate covariance of xy as sigma x minus x bar into y minus y bar, which is 122 divided by total number of units is 15. So 122 divided by 15 is 8.133. So correlation coefficient is covariance of xy divided by standard deviation of x into standard deviation of y. So 8.133 divided by 3.01 into 3.03. So we will get 0.8917. So here the correlation coefficient is positive, and see, if you take the result as correct to 2 decimal places, we will get the answer or the correlation coefficient as 0.89. Another example, find the Karlpearson's coefficient of correlation from the following series of marks secured by 10 students in a class test in economics and statistics. Marks in economics is given and marks in statistics is given. So I am taking x as the marks in economics and y as the marks in statistics. So I am preparing a table like this, the given x values and the given y values. Here I am using another method, like in the step deviation method we have studied for the arithmetic mean and for the standard deviation. Correlation coefficient is independent of the change of origin and the scale. So I can use the step deviation method here. So taking u as x minus 65 divided by 5. So 45 minus 65 is minus 20 divided by 5 is minus 4. And 70 minus 65 divided by 5 is 5 by 5 1. 65 minus 65 0 by 5 0. 30 minus 65 divided by 5 is minus 7, and so on. And this is the sum of all these u values, minus 8. Similarly, we are calculating v as y minus 60 divided by 5. So 35 minus 60 divided by 5 is minus 5. 90 minus 60 divided by 5 is 6, and so on. Now this is the sum of all the v values. Since the correlation coefficient is independent of the change of origin and the change of scale, the correlation coefficient of variables x, y is same as that of the correlation coefficient of uv. That is why we are doing like this: square this u values and we'll get the u square column, and the sum of all these is sigma u square is 146. This is the square of v values, and the sum of all these sigma v square is 182. Now multiply the u and v values, will get uv, and find the sum of all these, will get sigma uv is equal to 135. Since the correlation coefficient is independent of the change of origin and scale, we can write Rxy is equal to RUV. So RUV is calculated as n into sigma uv minus sigma u sigma v by square root of n into sigma u square minus sigma u square into n into sigma v square minus sigma v square. By substituting the values, we will get Rxy is equal to 10 into 135 minus 8 into 8 divided by square root of 10 into 146 minus 8 square into 10 into 182 minus 8 square. So by calculating this, we will get the value as 0.9031. Here the correlation is positive and almost near to 1, which means there is a strong positive correlation. There is a strong positive relationship between the variables. Now let us see the properties of correlation coefficient. The limits of the correlation coefficients are -1 and +1. That is, the value of the correlation coefficient lies between -1 and +1. R is equal to +1 implies perfect positive correlation. R -1 implies perfect negative correlation between the variables. If R is positive, the two variables move in the same direction. A negative value indicates the inverse relation. That means if one value increases, the other one decreases, or vice versa. When the price of a commodity rises, its demand automatically falls. A high value of R indicates strong linear relationship, and R is said to be high when it is close to either +1 or -1. A value of R close to 0 indicates that a weak linear relationship, but there may be other types of non-linear relations. If R is equal to 0, the two variables are uncorrelated. There is no linear relation between them, but other types of relation may be there. Correlation coefficient has no units. It is a pure number. The two independent variables are uncorrelated, but the converse is not true. Correlation coefficient is independent of the change of origin and scale. That means if x and y are the two variables, if we take u is equal to x minus a by h and v is equal to y minus b by k, where a, b and h, k are the constants and h and k greater than 0. In this case, if we calculate the correlation coefficient between x and y, that is same as that of the correlation between u and v. So in this session, we have seen the three different formulas for calculating the Karlpearson's coefficient of correlation, and what are the limits of the correlation coefficient, which lies between -1 and +1. And another important property of the correlation coefficient is it is independent of the change of origin and scale. So based on these three formulas, we can calculate the Karlpearson's coefficient of correlation. With this, we are concluding this session. In the coming sessions, we will see the Spearman's coefficient of correlation. Thank you.